Welcome back class to the lecture on machine learning. Last time we were discussing the logistic regression. We were halfway through. We discussed that logistic regression, it is based on the sigmoid function. And sigmoid function is basically you can say a slope like or S shape, a deformed S shape, and its value changes with the Z, which is equal to the theta x. So z is basically what we said, that it is over same value we saw previously, theta x. Okay, and its value changes between 0 and 1. So minimum it is 0, maximum it reach 1, it's 1, but it never is equal to it is never 100% equal to 0 or 100% equal to 1. It always reaches very close to it but never touches this line. So we discussed that in linear regression we had seen the hypothesis, which was simple. H was equal to theta 0 plus theta 1x. Okay, and then we said that to make it simple we ignore this theta 0 term and we only use theta 1x. So here we are using the same theta 1x, but this time because remember, in linear regression our output, the h value, it can be any straight line like this. But here we are not interested in straight line as an output. Our output should be some value between 0 and 1. So either 0 or 1. So we want to predict the output or the class of the output. So we practically need a floating point number between 0 and 1. So for this purpose, what we do is we use a sigmoid function. So we provide this theta x as an input to the sigmoid function g. Okay. So what does g do? G is basically represented by this equation 1 over 1 plus e to the power minus z. So if you know from your mathematics, e is just a constant. E is nothing but it's a constant, and it is equal to, so its constant value is 2 point, it's not writing, 2.71 something. Okay, so just like pi or any other number, it's a number and its value is equal to 2.71. Okay, so based on this, you need to predict an output or a class, either class, for example, if it's the cancer detection, you want to predict there is this cancer patient, the cancer disease for this patient, is it dangerous or not dangerous? So we discussed last time previously that not dangerous we represent it, for example, by 0, and the dangerous class we represent by 1. Okay, so how to predict it? Because over here the value that comes out from this function, the h value that comes out, it's a floating point number. So what we do is that we put a middle value as a threshold. So we have h when it is greater than or equal to 0.5. We will say that we will predict h as the output as 1. Or other case, when the h is less than 0.5, then we will predict our output as 0. So this is what we do. We want to predict based on this principle. Now, one important thing, that this relation between h and the theta x, remember theta x is same as z, so I will call this z. So there is a relation between this h and the z value. Whenever the h is greater than 0.5, practically your z value is greater than or equal to 0. You can test this yourself also. Okay, let's try it. So for example, here I should erase it, and here I make some space. So for this formula, let's say initially you have got the z value, let's say the z value you have got is very small, or let's say I discuss three cases. Okay, so let's see the z value 0. So when the z is 0, in that case you will have this g function which will be equal to 1 over 1 plus e power 0. Okay, e power 0. So how to find it out? So I will go out. Can I do it without going out? The calculator. Yeah. So the calculator, I take it out over here. So the e is given over here in the calculator, 2.7182 something, and you take the power of this. So e power 0, that gives you a 1. Okay. So now you can do it simply. 1 plus 1, it is 2, and you all know that 1 over 2 or 1 over 2 will give you 0.5. So when z is 0, in that case you will have the h value which is 0.5. Now take another case where the z is a little bit bigger. Let's say it is 0.1. Okay, so it's on the positive side. So when the z is on the positive side, what will happen? In that case, put over here in this equation e, and remember the equation already contains a negative sign with z. So e, and then you use the power, and on for the with the power you will be using 0.1 but with a negative sign. Okay, so it will give you this value for this expression e power minus z. It will give you 0.9. Okay, so let's use this. I will put add 1 in this number. It will be 1.90 something, and then I take the inverse because it is 1 over this value, so I will just take the inverse, and that will give me 0.5249. So I can just simplify and say 0.52. 0.52. Clear? So you saw when z is 0, the h value is 0.5. When z is more than 0, positive, then h value is more than 0.5. And in the last case, when z is negative, a little negative. So remember, I showed you a little positive value, but it is same thing. When z becomes very high, then the h value will be much higher than 0.5. So when z is a little less than 0, the h value will be how much? So let's calculate again. So here I will take again the e, and this time with the e I will put over here e power. So we will have e power minus minus 0.1. So minus and minus 0.1 will become plus 0.1. So I will have e power 0.1 with no negatives. So it will give me this number. So this time you see, last time the number was 0.9, now it is bigger than 1. So it is 1.1. You add 1 to this number. So it will be this number, and you take the inverse, and that will give you 0.47. So with this you see, you are getting the h value which is less than 0.5. So you can easily safely you can memorize this thing, that keep it in mind that whenever the z value is greater than 0, greater than or equal to 0, your h will be greater than or equal to 0.5. And remember, 0.5 is our limit or threshold. It means that whenever z is greater than or equal to 0, you will predict y as the output as 1, class 1. And whenever for the opposite case, when z is less than 0, negative, then in that case you will predict the class as 0. Clear? So pause the video, look on, carefully observe these concepts. If you have questions, ask in the group. Okay, so this is the crux, the basics of this logistic regression. I hope it's clear. It will be used in the next equations also. So here it is. I have got an example. For example, I have got the patients and the result from the patients, and I have two variables x1, x2, and here I have plotted the cancer patients. The circles, they represent the patients whose disease is not so dangerous, and the cross, it shows the patients which have the y equal to 1 category, where their disease is quite deadly. Okay, so I want, for this thing, for logistic regression, I want to create this pink line that will separate the two classes perfectly, as perfect as possible. Okay, so what I do over here is, you see that maybe, so this is just an example, maybe our h in this case will be represented by the sigmoid function of this linear formula. Okay, always we use the sigmoid function in logistic regression, because sigmoid function, it gives you the output value for h, which is between 0 and 1, and that you can easily convert to the prediction for the classes, for the two classes. So from this formula, now I can use the previous concepts we have seen. You see this g of z. So over here you see this whole thing over here. This is a z. So if you remember previously, we discussed that z, if it is greater than 0, greater than or equal to 0, then in that case I will predict y equal to 1. So that's shown over here. So y equals to 1 if this, so what you see over here, theta 0, theta 1, theta 2, all of these things over here, I am giving just an example. So theta 0 has minus 3 value, theta 1 is 1, and theta 2 is also 1. So these are just some sample values, just to show you, just to give you an example. So if the equation is like this, minus 3 plus x1 plus x2, so for my prediction y equal to 1, I should have this equation value greater than or equal to 0. Now what is the advantage of this thing? By this formula, we have clearly created a link between the variables, input variables x1, x2 with the output class. Okay, so whenever x1, x2 value is such that the overall equation value is greater than 0, then output class predicted is 1. So that's the advantage. You can simplify these things further. So with this equation, so this is an inequality. You can clearly transform this inequality into other. So you see over here you have minus 3. You can easily add plus 3 on both sides, or you can simply say that I take this minus 3 on the other side, it will become positive. So it is x1 plus x2 greater than or equal to 3. So this is it. This will give me a line, this thing over here. So this will give me a hyperplane. Okay, the line that will separate the two classes, it will be the line, this one, x1 plus x2 equal to 3. On one side of the line I will have this equation y equal to 1 class, and on the other side of the line I will have the y equal to 0 class. Okay, so remember, on one side of the equal to line I will have these values, y equal to 1. So line itself is also included in y equal to 1. So if there is a point that exists on this line over here, that will be part of y equal to 1. So others, the values that are coming below this, they will be predicted as 0. That's how it works. And the beauty of this logistic regression is that it is a highly explainable algorithm. There are many more concepts, many more algorithms that are used in machine learning. Many of them are not easy to explain. You cannot give any explanation. In the future chapters, for example, you will see neural networks, and they are not easily explainable. So you cannot make a relation between the input and the output. But here for this logistic regression, It's very highly explainable, and we use the term that this algorithm is easily the output is easily understandable, or the relation between the output and input is easily traceable. Okay. Sometimes the decision boundary will not be something that can be represented by a straight line. So for example, if you see over here, this over here is the pink line you see over here. That's the pink boundary that you see over here. It's not a straight line. Okay. So any straight line you take, it will never be possible to separate the two classes, the red cross and the blue circles. You cannot separate them by a straight line. So in that case, you need some sort of non-linear behavior or non-linear function. And the non-linear function that is used over here is shown by this equation. And one very useful trick that the people use is that they take the existing features. So remember, we have features as inputs. So if I have only two features, and I want to use them, so for example, the size of the cell and maybe some other feature, the color of the cell, I don't know, in the case of cancer problem. So I can use those features to create some new features. We discussed it earlier in the class. So how to create new features? You just take another, you just append or add another equation where you have the uh, these features squared, for example. So you add theta 3 plus, no, theta 3 into x1 square. Then there is theta 4 into x2 square. So like that, you can add even more terms which are higher order terms. So these terms over here, they make this function non-linear. This is not a line, and this is no more a line, a straight line or a plane. So here you see, so in this case, for this thing, it will be represented by some non-linear equation, and if you see this circle, this is represented by this formula in pink. So x1 square plus x2 square equal to 1, where 1 represents I think the radius of this circle. So like this, we can have non-linear and linear decision boundaries. So uh, if my circle is represented by this formula, we can say that when y is, we will predict the y equal to 1. We will predict the outside red class when this function has a value which is greater than 0. Okay. From where this comes? This thing comes from this formula, the equation. Equation represents this boundary only. So anything outside this boundary is represented by greater than or equal to 1. Okay. And then you modify it, you will get this thing greater than equal to 0. Clear? Similarly, you can have any other function, maybe way more complex. You can append or you can use any combination of terms together to create some very complex. So for example, you can have the terms like x1 square x2, or x1 square x2 square, or x1 cube x2, and so on. There are a large number of possibilities, and these functions will be very efficient in representing some extremely complex or irregular shapes. So here you see one shape where the y equal to 1 is enclosed inside an irregular shape or irregular boundary, and outside this boundary y is 0. Clear? Pause it. If you have questions, you can always ask. So this was the introduction about the logistic regression and how the decision boundary is used. So we don't in linear regression we use the linear equations. Here we are using linear equation in combination with the sigmoid function. But linear equation is only used when we want to separate the two classes by linear by a line or a plane. Okay, but if the classes are not separable by a straight line, then in that case we will be using non-linear functions. One other thing that we saw previously was when we create a line, when we create the hypothesis function, the next thing that comes is to calculate the cost. Why we calculate cost? So if you remember, we calculate the cost. That gives us the idea that how much my hypothesis H, it is closely representing my output, the previous output. That's why it's called supervised learning, because we have lots of previous examples that we can use to fine tune or to correct our hypothesis, or to correct our tunable parameters theta 0, theta 1 in the hypothesis function. So here the cost function, it's different. It's not the one that we saw in the linear regression. If you remember, so here it is, you see that we have seen this discussion many times in the last chapters. We have a training set where we have examples, input values x, and then the output is given y. We put a number on the top of these to show the example number, the row number. Okay, so if we have m examples, these examples will help us to train our model. So we have m examples, and over here the hypothesis function with us is this function 1 over 1 plus e power minus theta x. Okay, the t symbol you see over here, this represents the transpose, but it's not directly relevant to us. It's only for, you can say, programming purposes. So how we choose this parameter theta? That is chosen by, you can say, iterative method. You can say hit and trial method or iterative method. We choose a random value and then we keep on improving that value. So for that purpose, previously we had in the linear regression, we had the cost function j, which was equal to, if you remember at that time, 1 over 2m sum of the errors, square of errors. So if you remember, the formula was something like this: 1 over 2m sum of ERR square. If you remember at that time we did it. Okay, and error, what we said at that time, so we created the table, and from the table we found out the error. It is basically the hypothesis minus the y value squared. So if it is the square of this value, so we don't care if it is h minus y or y minus h. Same thing. Here in our case, so this was the previous one, the cost function. And remember, the cost function that we saw, it depends on the shape of the, it will give us some sort of shape for the j value. And if you remember, you plotted the j value, the cost function, on y-axis, and then we put the theta value on the x-axis, and it gives us the it gives us a shape which was, in the case of linear regression, it gave us a convex shape, a bowl shape. So bowl shape was given, and we said that if we try changing the theta values based on gradient descent, it slowly improves. But we also discussed that there are some other shapes that are also possible for the j function, which can be non-convex. So convex is something that is like a bowl, but non-convex will be an irregular shape which can go up and down, so not like a bowl. So it can, even here they did not show, but it can be any irregular shape. It can go up or go down. Okay. So in the case of logistic regression, what type of shape we will have over here? So logistic regression cost function, it is represented by two important things. Okay. To explain it first, we need to look at so this is a little bit difficult. To calculate the logistic regression cost function, we need to know one important concept. Let's say in your example that was given to you, you have a y which is equal to 1. Okay, and based on your h value, so you have an h value, remember h is a floating point number, so let's say you have an h value 0.72. Okay, so when you have 0.72, you will predict the output as 1. So your past example was 1 and you predict, so predict, okay, you predict 1. So do you think there should be uh, any cost or any penalty? No, because the output was previously 1. You also predicted that the output should be 1 and you shouldn't be penalized. But in this approach over here, if the output in the example was 0 and you predicted it with the 1 with a high probability, then you will be penalized. Okay, then there should be some sort of fine that will force you to correct or force your algorithm to correct itself. So remember, same was the case over there. When there was, if you remember in the linear regression, the j value that you calculated, it was depending on the error square. So if the error was high, your j value will be bigger, and then you used that j value to calculate changes in theta, if you remember. Okay, how you calculated changes in theta, that is not given here, it will come. Okay, so now in this case, how do we calculate the error? That is different. Why? Because the output has two different values. So in the past, if the y is 1 and I predicted 1, then the error should be almost nothing. But if the output in the past y equal to 0 and I try to predict it as 1, now that's a big problem. So the error depends on the value of the y. Okay, so if the output y, the previous old value of y and my prediction, they are same, there will be low error. Okay, if the output y does not match my prediction, there will be h, high error. Okay, same is the case on the other side. Okay, what is the other side? If the y value is 1 and I predict it to be 0, okay, and so I have a prediction 0.1, for example. If the y in the old examples it was 1 and I predict it to be 0.1, which means that I will say that it's 0, then it's a big problem. It will be a high cost. So I write h, h means high cost. Whereas if y is 0 and I predict it 0.1, that means I almost am correct. I will predict it to be 0. So my prediction 0 will be same as y equal to 0. So cost will be low. Even if the y is 0 and I predict it as 0.1, finally this 0.1 will become the value 0. Still there will be some cost, some error. Why? Because I am not sure about my prediction. Y is 0, but I have, because remember 0.1 and 0.4, they are not same. Okay, 0.1 means that I am quite sure, I am very sure that it is 0, but 0.4 means that I'm not so sure about this value. So it's a little difficult concept to grasp. So pause it, think over it. What is happening over here is that my prediction will be checked against the actual value of y. If the actual value of y is 0 and I predict it as high, so the more higher I predict it, more cost I will have. So if I predict 0.7, then I have a high cost, but if I predict it 0.99, then I will have the maximum cost because I am too much wrong. Whereas if I have, if the actual value of y is 0 and I predict it as 0.1, I will have almost minimum cost. But if y is 0 and I predict it as 0.4, still my answer is correct, but because I am not sure about my answer, that's why I will get some cost, I will get some disadvantage. Is it clear? So this is very important concept, and how we implement it in terms of one formula. So remember, in the case of linear regression, we have a one big formula, 1 over 2m sum of error square. Here we have got two parts of the formula. So the cost h, the cost function j, it depends on two things. So it has an equation has two terms. One term is when y is 1 and one term is when y is 0. Okay, so when the y is 0, in that case whatever value I predict, let's say first when y is 1, in that case whatever value I predict, I take the log value of that. So if I predict with 0. So let me show you on calculator. So let's say y is 1 and I predicted it as 0.95. Okay, so the value over here that will come out will be the log, I think this is the log 2. So how should I put the log 2 in this formula? So I don't remember, I don't know if it is log 2 or I think it's log 10, log base 10, but still let's see. Okay, if we divide it by log 2, then it will give me this. Okay, minus 0.074. So if, so just to give you a comparison, if y is 1 and I predict it as 0.95, okay, how much penalty I am getting? Penalty I am getting is 0.0 and how much? 0.07. So 0.074. Now I give you another example. Y is 1 and my prediction is still 1, but it is 0.55. Okay, in that case what will happen? So again, take this, I will put over here the h value, I will be having 0.55, and then I take the log of this value. Okay, the signs I haven't taken care of. So if you want to take care of signs, it is like this, negative, and if I put, so remember this is log 10, but if you remember I discussed in the class that if you divide it by log of 2, then it will give you the answer in log 2. Okay, now the answer this time it comes out 0.86. 0.86. So you see, both times my hypothesis value output, it comes out to be class 1. But based on my confidence or based on my closeness to the 1, I will get different error values. Okay. So when output y class is 1, if I say that it is 0.95, it's quite close to 1, I will still get, because I am not 100% sure, okay, I will still get some error value which will be 0.074, very negligible, very small value. Now if on the other side, if y is 1 but I predict it as 0.55, okay, now this is it's a positive class, I predict positive, but I am not so sure, because remember, if it is less than 0.50, it will become class 0. So because I am not sure, I will get a huge fine or penalty. So the fine or the error value I will get over here, it will be 0.86. 0.86 is much bigger as compared to 0.7. Okay. Now let me take some extreme value on the other side. Y is 1 and I predict the hypothesis, my hypothesis predicts it 0.1. Now this is a disaster. This is on the opposite side. It is a wrong prediction. So how much will be the fine? Okay. So when y is 1, and this time what I want to do is that h is 0.1. So let's take 0.1. I take the log of it, minus 1, and negate it because of this minus, and then I will divide it by log of 2. That will give me the answer in log 2. So the error value this time I am getting is 3.32. Too big, and this will hugely impact my overall error value. This will hugely impact finally the theta value I will change. Okay, remember, if j is too big, it will change theta that much. So remember this concept, j will affect the theta. That's the same concept we had from linear regression. So overall what's happening over here is that my h value, whatever prediction I am making, that will be making an effect on what error I have. The same concept is done below for y equal to 0, but only difference is I am subtracting it from 1. So when I subtract it from 1, it is almost the same thing, but now I am caring more about 0. So for example, if I predict 0.1 when y is 0, so 0.1 means 1 minus 0.1, which means 0.9. Okay. So practically I am converting it. You can say when I am doing 1 minus this value, I am just, you can say, inverting it. Okay. So let's do one example. So when y is 0, okay, and y is 0 and I predict it, again I will take these three values, 0.95 and 0.55 and 0.1. Okay. So in the case of 0.95, what will happen? Now this time 0.95, the value is not passed to the log function. The value that will be passed to the log function, it will be 1 minus 0.95. So 1 minus 0.95, it is 0.05, that is the value I am passing to the log function. So when I take the log of this function, it is minus 1.3, take the negative and then divide it by log of 2. So it will give me the fine or the error value of 4.32, which is very big. Okay. Now again, let's say I choose another value, which is 0.55. So again, when I do 1 minus 0.55, it will give me 0.45. I take the log, I divide it by log of 2, and this will give me, so I remove the minus sign. Okay, it will give me a value of 1.15. So 1.15. Still I have a big error value because you see over here I am predicting it wrong, the wrong class. Okay, and when I predict it quite, so in that case I have 1 minus zero point 0.1, so it will give me 0.9, and 0.9 I take the log, negate it, and also divide it by log of 2. So it will give me 0.15. The error over here is 0.15, which is comparatively quite less. It can even improve if my error value goes more down, it will improve. So you see over here we have got these three error values. The more closer I am to my prediction, it does not depend on only on the class, what class I predict. It depends on how much confident I am in my prediction. So more closer I am to the more closer my prediction is to the actual class, the lesser will be the fine value. Error will be higher if my prediction is much different from the actual class. This happens in both the cases. So both the cases you see the error values, they change. I hope this is clear. You can pause the video, you do it on the page yourself. That's the key. If you don't do it on the page, you will forget it. You will not understand. So overall, what happens for y equal to 1 case? So let me So overall what happens if for y equal to 1? So when the y is 1, in that case what we are doing is, when y is 1, in that case if you remember, the practically y is 1, and more your h value is close to 1, the error will be less. Okay, so for example, if your h value is 0.95, we saw that in that case when it is h is 0.95, your error will be quite less, negligible. So it was, I think in our case it was 0.07. But if y is 1 and you are predicting it close to 0, in that case your error value will shoot, it will become very high. So overall you will get this curve that you see over here that represents the error for y equal to 1. So remember, I told you in logistic regression you will have two cases. Okay, so this is the first case. So your cost will be 0 if class y is 1 and you predict it 100% as 1. So if you predict h equal to 1.0 exactly, then you will have 0 error. Okay, but if you go even a little bit down from 1, so let's say y is 1 but h is equal to 0.99, 0.99 is very close to 1, but still you will have some error value. And theoretically, if the y value is 1 and you predict it as 0.0, then in that case theoretically your cost will be infinite. But practically we deal with it with some very high penalizing. Okay, so we capture the intuition that if h is 0, we predict it as 0. So when we are predicting it h is 0, but the output class itself was in the past data, it was 1, we will get the maximum penalty, very large cost. Okay. Now come to the opposite case. We have discussed this also. When y equals to 0, in that case what will happen is that y is 0 and you predict it as the close to 0. You say that this is 0.1, h is 0.1, then you will have a very low error. But as the h value goes higher and higher and higher, more close to 1, your error will shoot. It will become too high, the error value. So overall our cost function has got two parts, log of h minus log of h and minus log of 1 minus h for two different values of y. So this is it. Go through it, ask questions if you have any. Very important concept. This is the main part of logistic regression. If you understand this concept, you understand the whole logistic regression. So we have seen this simplified. What we see next is we will see how we can use it. Try to simplify it and then we will use it. So we saw earlier that the cost function j, it is you can say the average of overall cost for each row. So from each sample value, each row, whatever cost you get, you take the sum and you take an average divided by the total number of rows. So here the cost we have seen, it is represented by this two-step formula. So there are two parts of this formula and it depends on y equal to 0 and y equal to 1. So overall we can write the j function as this formula. So what I have done over here, so if you see, look at this j formula, I have got this log of h, this log of h, I multiply it with y. Why I multiply it with y? Because when y is equal to 1, I will be using this formula. When the past value of y is 1, I use this formula. Okay. If the y is 0, y will be 0, this formula will automatically become 0. On the other side, I will be using 1 minus y and then log of 1 minus h. And whenever y is 0, I will have 1 minus 0. So I will be using this formula. So these two values, 1 y and 1 minus y, they are just like the selectors. Okay. So, something similar that maybe in logic design you used to see the multiplexer. You select first input or the second input. So same thing is happening. They have no other rule. They have no other role in this formula, only to select either this equation, or this part of the equation, or that part of the equation. Okay. So when y is 1, it will select this one, other will be 0. But when y is 0, so y is 0, this part will become 0. But when y is 0, this part will be 1 minus 0, which is 1. So this will be activated. Okay. So this cost function is an intelligent combination of two separate parts. Okay. So when y equals to 1, you see that it will be minus log of h. And when y is 0, it will be minus log of 1 minus h. Pause the video and go through it. Do it yourself. You will see it's very simple. At one time, only one of the functions will occur, because remember, these two parts of the function, they depend on y, and y is a binary value. It's not like h. It's a number, either 1 or 0. Okay. So here is the formula, more neatly written. So the j formula, it will be equal to this thing, and plus 1 minus y into log of this, and overall we put a 1 over m. 1 over m is for averaging. I discussed earlier, it is for averaging. And the minus that was inside, so remember you have a minus over here, minus y log h, and then you have minus 1 minus y log 1 minus h. The two minuses, I take them out, and they are commonly shown over here, minus 1 over m. Okay, so we use this, and we find out the value of j, and then we try the values of theta that can minimize the j, and then we can use this to get the best value of theta. The minimum j will give us the best value of theta. Same theory as we have seen in linear regression. That theta will be used to predict for the future. It will then be used to predict what will be y. Okay. So the formula here given py equal to 1, this is only to show you we will use theta to predict. So how gradient descent will work? Gradient descent will work in the same manner as it was for linear regression before. So here you have this j formula over here. This j formula, I will use it I will try to minimize this j value, and to minimize the j value, what I will be doing is that every time I will tune, or I will increase or decrease the theta a little bit. And how much value I will change in theta, that depends on the gradient of the j. So I have got the derivative I take for j, multiply it with the alpha value. Alpha, if you remember, it is the learning rate, and whatever value comes out, I take this and I subtract it from theta. Automatically it will adjust for adding or subtracting. It will automatically adjust, and I will do this update for all the values of theta. Okay, so the derivative of j that we take over here, if you remember in the last chapter linear regression also, the derivative of j, it will come out for us to be this thing, which is h minus y into x. So we repeat it, and you see over here we simultaneously change the theta values, and we have this formula, theta minus alpha times this error function, and error function here is h minus y into x. At this point, the algorithm, it looks similar to linear regression. Okay, go through this page. If you have questions, pause and absorb it, and then ask questions. So the cost function j, till now we have seen it. We want to minimize the j, and for this we try to tune the theta value, and theta value we try to adjust, make changes such that the j improves. So how much theta value we change, it depends on the derivative of the j that we take. The derivative what we get, that derivative we add or subtract from the theta value, and we do it repeatedly. That's what is called as gradient descent. So gradient descent is an iterative approach or a repeated approach, where we repeatedly subtract the derivative of j value from theta until it converges. So the whole theory we have done so many times. I hope you don't have any trouble with it. So what optimization algorithms we can use? This one you have seen, gradient descent, but there are some other approaches also which are possible. There are many other methods we will not cover in this course, but we only focus over here on gradient descent. Okay, there are many other advantages which are more complex. The biggest problem with them is they are complex, but they are faster than gradient descent. And in those approaches, you don't even have to worry about the alpha value, which is the learning rate value. You don't have to worry about it. So here is an example. So for example, so this is just one thing we show over here. For your theta values, let's say you get this j function. Okay, the j, the cost is represented by this equation or formula. So you can take the derivative with respect to each. Remember, the partial derivative is taken with respect to one parameter at a time. So partial, it is called partial because we take the derivative, for example, for one variable, and the other variables, they are kept constant or fixed. So this partial derivative is with respect to theta 1, and at that time theta 2 is constant. So when you take the derivative of this, so derivative of this equation, this term with respect to theta 1 will give me 2 times theta 1 minus 5. So if you remember the derivative formulas, this is the application. But because the derivative is with respect to theta 1, so there is no theta 1 term in this equation. So for derivative of with respect to theta 1, this is a constant. It's not changing. So constant, the derivative of a constant is 0. So this term becomes 0. Okay. So it is 0 over here. We don't show. Similarly, for the other case, when we try to find the derivative for theta with respect to theta 2, it will come out to be 2 times theta 2 minus 5, and the first term will become 0. Okay. So both the functions, they will subtract different values from their respective theta 1 and theta 2. Okay. Leave this implementation, code implementation, leave it. And so this is just an example how we work on these things. Leave the code part. We are not interested in the coding side. One last topic from the logistic regression that is left. It is related to multi-class classification. Till now we have seen only two classes, good class or bad class. Or one class we call it 0, other one is 1. Or one is, for example, in the case of cancer, one was less dangerous and the other one is more dangerous. There are some cases when we have multiple classes to find out. So multiple classes, for example, can be, for example, in the case of email problem, instead of spam or and not spam, we have a problem where each email that comes, my algorithm has to decide which folder it belongs to. The email, it is related to my work, it is related to my friends or family, or it is related to some hobby or some interest that I have. So 4 classes. And another example for multi-class classification can be in the case of medical problems. If there are 2 classes, they can be sick or not sick, but there can be other more than 2 classes. For example, not sick or not ill, and then there can be class of person has cold, or person has flu, or person has sinus problem, for example. So there can be many classes. Similarly, for the weather, you can have multiple classes: sunny day, cloudy day, rainy day, snowy day. So there can be many classes possible. So all these classes we can put over there the numberings, starting maybe with 0 or maybe with 1. So you can have y equal to 0 or 1, or y equal to 0, 1, 2, 3, or y equal to 1, 2, 3, 4, or so on. So in the binary classification, the task was simple. You have 2 classes, you separate it with a line. Now in the multi-class classification, you have 3 classes, and hopefully there is some sort of separation possible between them. But how to do this? That's the problem. For this purpose, what we do is that in the simple binary classification, you used a simple straight line to divide them. Here what we do is that at one time we only focus on one class, and we call this approach as one versus all, or one versus rest. So at one time I focus on for example these green triangles, and I say that the other 2 classes, they are not green. So this is green, others are not green. Okay. So in this case my map will become like this. green, and not green, maybe you can give it any shape. So I can easily make a decision boundary. Okay. Similarly, second time you will decide the boxes, blue boxes, and you say that one class is blue boxes and the others are not blue boxes. So we are solving the multi-class classification problem by converting them into multiple binary classification problems. Okay, so I have three classes. In one problem, I have three classes. I can solve it by using three different. I can divide it into three different parts, and each part is a separate binary classification. So the third one is this, where I have this cross, red cross, and the other side of the class is not a red cross. So basically I have three classes. I divide it into a problem of three separate binary classification problems. Clear? So it is a typical prediction. So on the right side, these are the typical problem that you have already done. It's the same. No separate theory. Same thing. This is how it works, and we call it one versus all classification or one versus rest classification. So here you'll see how it works. Every time we draw a line, we separate it from the rest. So we only separate that class in which we are interested in. We don't care about the others. So how it works? We train a logistic regression classifier H for each class I to predict the probability of this class. So on new input X, we try to make a prediction and pick the class I that maximizes. So when a new value comes, for example, okay, so for example, a new value comes and the new value lies over here. So this is my new value. Okay. Now what happens is that when my model has been trained, in that case, I asked each of the model, give me the answer. Okay, give me the answer, please. So for each model I ask, the first model it says it is class number 1. Second model says it is not class number 2. Third model says it is not class number 3. So it is not class 3, not class 2, but it is class 1. That's it. Simple. It's done. But only difference is that multi-class classification, you will run 3 separate models. You will do 3 separate evaluations each time. So like this you will do it, and you will try to maximize your prediction. So we finish over here our chapter. In the next class I will try to show you some examples on the scikit-learn, how to do it over there, the details of practical.